Hello everyone, welcome back. We are going to work on module 6, which is chemical reactions and stoichiometry in this next couple of lectures. So I will start sharing my iPad so we can get ahead, go ahead and do that. Okay. So in a chemical reaction, we have chemical changes in matter, which result in new substances. If you recall, chemical changes indicated that the chemical identity of the substance that was undergoing the change changed and resulted in a new substance. So reactions involve the rearrangement and exchange of atoms in order to produce new molecules. Elements are not transmuted, which means uranium doesn't turn into gold, right? If I have lead, I have going in, I have lead coming out. If I have carbon going in, I have carbon coming out. Remember, I'm breaking bonds, rearranging atoms, forming new bonds, and that's how I get new molecules as my products. So this is basically the format down here. On the right side of my reaction arrow, I'm going to list my reactants. On the left side of my reaction arrow, I'm going to list my reactants, and then on the right side, I'm going to list my products. So here's an example using molecular diagrams. Here, I have two hydrogen molecules, which are those guys. And then I have one oxygen molecule, which is this guy here. That's reacting to form two molecules of water, the H2O, and then I'm getting some energy out of that as well. So the hydrogen gas and the oxygen gas are my reactants. My water and my energy are products. So the overall definition of a chemical reaction is the transformation of one or more substances into different substances. This is the type of reaction format that we're going to be using the most, where I have my reactants and the number of molecules indicated for both on the right or on the left side, and then I have the products, the number of products that are produced on the right side. So chemical equations are actually a shorthand way of describing a reaction. They provide a lot of information about what's happening. I have the formulas of the reactants and the products. You need to know your nomenclature, because if I say the product is water, you as a chemist need to know that the product formula would be H2O. If I say sodium sulfate is reacting, you need to know what the formula of sodium sulfate is. We also indicate the states of the reactants and the products, and that's going to be whether it's a solid, a liquid, a gas, or if it's an aqueous solution, which means it's dissolved in water. And then we have the relative numbers of reactants and products that are required. And this can be used in our mathematical treatment of what happens within a chemical reaction, which is the field of stoichiometry. These are the states that you have to know. The little g in parentheses is gas, the little L in parentheses is liquid, and the little S in parentheses is solid. This is aqueous, which means it's in a water solution. These are the four states that you're going to see. A real chemical reaction isn't complete unless I indicate the states of the reactants and the products, although many times people take shortcuts and you'll see a lot of reactions where those states are not indicated. So these are my chemical equations, right? Right here is the chemical equation. I use chemical formulas, and that's going to give me the identities of the substances, both the reactants and the products. This is a coefficient. This is a coefficient. This is actually a 1, because if there is no coefficient, the coefficient is assumed to be 1. And my coefficients are going to indicate quantities of substance that are involved in the reaction. So let's look at the combustion of matter, or the combustion of methane. Methane gas burns in the presence of oxygen to produce carbon dioxide gas and gaseous water. Remember, whenever something burns, it's combining with O2 gas. If you look closely, you should immediately spot a problem. On the reactant side, I only have 2 oxygen atoms, and on the product side, I have 3 oxygen atoms. Well, there's a law that we learned about that would expect you to have the same number and type of atoms coming in as going out. This reaction, as written, does not obey the law of conservation of mass. Notice also that I have 4 hydrogens on the left, so the reactant side, and I only have 2 hydrogens there. Again, this is not going to obey the law of conservation of mass, because what goes in has to come out. So I have to have the same number and types of atoms on the reactant side as I do on the product side. So to correct these problems, we're going to balance the equation. And to balance something, I change the coefficients of the reactants or products. I'm not changing the subscripts. Remember, these subscripts are dictated by bonding rules. I can't change them, otherwise I have a different identity of the substance. But I can say I need 2 methane molecules, or I need 5 waters. I can change my coefficients, and I'm going to try to do this so that what goes in comes out, and all of the number and types of atoms on the reactant side are equal to the numbers and types of atoms on the product side. So I'm going to use the law of conservation of mass in order to balance this reaction. We're going to adjust the numbers of molecules so that there are equal numbers of atoms of each element on both sides of the arrows. So here I have 1 carbon plus 4 hydrogen plus 4 oxygen. And that's because I put a 2. This is like the distributive property. I have 2 oxygen molecules. If I look, I change the water to 2 molecules. Again, that gives me 4 hydrogens and 2 oxygens. This gives me 4 oxygens. So what I get then is, on the right side, I have 1 carbon, 4 hydrogens, and 4 oxygens. On the left side, why do I keep turning that around? On the left side in my reactants, I have 1 carbon, 4 hydrogens, 4 oxygens. And on my right side in my products, I have 1 carbon, 4 hydrogens, and 4 oxygens. Well, the mass of this is going to equal the mass of that, because I know the masses from the periodic table. So this does now obey the law of conservation of mass. So there's a 4-step method on how to balance chemical equations. It all hinges on writing the correct formulas for my reactants and my products. And I'm going to include my physical states. You're going to check whether the expression is balanced by counting atoms on each side of the reaction. You're going to balance any element that appears in only one reactant and product first. And then you're going to choose coefficients to balance other elements as needed. This isn't a very difficult task, but sometimes it does take some practice. So let's look at this reaction. I have carbon, hydrogen, and nitrogen. I have carbon, hydrogen, and nitrogen. On the reactant side, which is this side, I have one carbon, I have one nitrogen, and I have 4 plus 3, which gives me 7 hydrogens. On the product side, I have one carbon, I have one nitrogen, but I have 2 plus 1, I only have 3 hydrogens. So this is not balanced. I have 7 hydrogens on the reactant side and 3 hydrogens on the product side. So how can I change my coefficients? Remember, I can't change subscripts. I can't make my 4 or my 3 or my 2, these subscripts. I can't change them. I can only change the number of those particular molecules. So let's think about that. Well, I can get 7. 3 times 2 hydrogens is equal to 6. And then I have this other one. So that gives me 7 hydrogens on that side. So if I have 3 molecules of hydrogen and I change the coefficient from a 1 to a 3, everything ends up balanced because now I have 7 hydrogens coming in and 7 hydrogens going out. Notice by changing the coefficient for hydrogen, I did not change the number of carbons or nitrogens because those atoms were not in the formula for the H2. So let's do this one to see if we get it. I'm going to count my numbers of atoms. I have 3 carbons on this side. I have 8 hydrogens, and I have 2 oxygens. On this side, I have 1 carbon, I have 2 hydrogens, and I have 2 plus 1 is 3 oxygens. So these guys, which are combustion reactions, I balance in the order of CHO. It makes it easier for this type of a situation to do that. So I'm going to put a 3 here. Oops, sorry. I'm going to put a 3 here in order to make my carbon balance. I made no changes to the reactant side, so nothing changes there. But now I have 3 carbons. I have 3 times 2, 6, 7 oxygens. My hydrogen and my oxygen are still not balanced. So how can I balance the hydrogens? I have 8 over here. How can I make 8 there? Well, if I put a 4, I have 4 times 2, that'll give me 8 hydrogens, but that changes the oxygen. So now I have 4 plus 6, I have 10 oxygens. This is an easy fix because I only have oxygen by itself on this side. So since every molecule of oxygen is O2, if I put a 5 here, that gives me 10 oxygens. So I have 3 carbons, 8 hydrogens, 8 hydrogens, 10 oxygens, 10 oxygens. By putting those coefficients as a 1, 5, 3, 4, this is now a balanced chemical equation. So that's what you need to know. You kind of have to go back and forth until you get a balanced chemical equation. Here's another one. Now, here's another trick. This is the nitrate ion. If my polyatomic ions are not broken apart, I can balance them at a separate unit. So here I have a sodium, I have one nitrate, I have one lead, I have one oxygen. I don't count the oxygens in the nitrate because they're here. On this side, I have one lead, I have two nitrates, I have two sodiums, and I have one oxygen. My sodium and my nitrate are not balanced. Let's do sodium first. If I put a 2 here, that gives me 2 sodiums. That also gives me 2 nitrates. Now, if I look at this, I have 2 sodiums, 2 nitrates, 2 sodiums, 2 nitrates. I have 1 lead, 1 oxygen, 1 lead, 1 oxygen. Just by doing that, one coefficient changed. Now I have a balanced reaction. Let's do the second one. I have 1 silver, 1 iodine, I have 2 irons, and I have 3 carbonates. I have 2 silver, I have 3 iodine, I have 1 iron, and I have 1 carbonate. So what is a quick fix? I could look at silver. I have 2 here. If I put 2 on this side, that gives me 2 silvers. It will also give me 2 iodides. But now I notice I have 3 iodides and 2 iodides there. So that is not correct. So let me try something different. What if I put a 2 here? That'll give me 2 iron, and that'll give me 6 iodines, or 6 iodines. Well, now I have 2 irons, 2 irons, I have 2 silvers, 2 silvers, but I still don't have the right number of carbonates. Notice I have 3 and I only have 1. So I'm going to put a 3 there. That's going to give me 4 silvers and 3 carbonates. I only have 2 silvers here and I only have 2 iodides. So can I fix this? Yes. If I have a 6 and I replace that 2, that gives me 6 silvers and 6 iodides. That gives me 6 silvers from this 3 times the 2, and I have 2 times the 3, that gives me 6 iodides. Now I'm balanced with a 6, 1, 2, 3. So this is now balanced. Sometimes you have to go back and forth and back and forth. When I change one part of the molecule, notice if I change the silver, I also change the iodine because those are connected. If I change the iron, I also change the carbonate because those are bonded together. So you have to pay attention to that. So notice this balanced chemical equation allows us to represent chemistry on different levels. I can have a microscopic reading of this equation where I have 2 molecules of hydrogen reacting with 1 molecule of water, and then I produce, or 1 molecule of oxygen to produce 2 molecules of water. So that is one way I can represent a balanced equation on this microscopic or molecular basis. There's another way, which is this macroscopic vision. Remember, if I'm doing this in the lab, I'm not going to be able to just use 2 molecules of hydrogen gas or 1 molecule of oxygen gas. I'm going to have to bring this into the real world. I'm going to have to bring this into that macroscopic world where I can actually see and mass and measure things in order to do this in a lab. So the way that we've learned to bring this very, very small submicroscopic molecular world into the world where I can see and measure and I can weigh and use glassware to figure out how much of any reactant or product I need, I'm going to use this mole translation. This can also be read as 2 moles of hydrogen gas react with 1 mole of oxygen to form 2 moles of water. This is the version that we're going to look at in terms of stoichiometry. Stoichiometry is going to be a mathematical treatment of how much of each reactant or product do I need or obtain in a chemical reaction. But remember, this is how that reaction actually occurs. It's molecules that are reacting. It's molecules that are having their bonds broken, and new bonds are going to be formed to form new molecules. This is what actually happens, but in order for me to do this on a lab scale, I have to bring it up into a quantity that I can weigh and measure and basically see so that I can do this in a lab. The next lecture that we have will deal with stoichiometry, and we're going to be using these coefficients, these mole ratios, in order to do stoichiometry. So with that, I am done for now, and we will be back in order to do the next part, which is using those moles in order to do stoichiometry. See ya.